So another application for these exponential formulas is the law of cooling. And it says a pot of boiling soup with an internal temperature of 100 degrees Fahrenheit was taken off the stove to cool in a 74-degree Fahrenheit room. After 12 minutes, the internal temperature of the soup is 87 degrees Fahrenheit. So the first part asks us to use Newton's law of cooling to write an equation that models the situation. And our general formula is going to be given to us over here, and that is T of t equals A times e to the kt plus t sub s. And we have what these variables stand for as well. So T of t is our dependent, and that's going to be the temperature of the object that changes with time. Then A is the difference between the initial temperature, which in this case is going to be 100, and the surroundings. So, and it says here that the room was 74 degrees. Then T of sub s is the surrounding air temperature, again 74 degrees. Then K is the cooling rate, and T is the time. So for part A, we know that the temperature was 87, so this is our T sub T, that 100 was the initial, and then 74 is the room, the surroundings, and then T is 12. So we can plug these in, whatever we know, into the equation, and we can solve for what we don't know. So we have 87 equals 100 minus 74 times e to the k times 12 plus 74. So if we subtract 74 from both sides, then we get 13 equals, and then we simplify this to 26 e to the 12k. And then if we divide both sides by 26, we get 1/2 equals e to the 12k. Take the ln of both sides. So ln 1/2 equals 12k. So k, our cooling rate, is going to be the natural log of 1/2 divided by 12. And then if we plug this into the calculator and round it, then we get approximately negative 0.0578. So this is our K value, our cooling rate. So our equation is going to be T of T equals 26 times E to the negative 0.0578 T, and then plus our T sub S, which is 74. So this is our equation, and we're going to use this to solve for part B and C. So part B asks, how long will it take for the soup to cool down to 78 degrees? So in this case, our temperature again is given to us, and we want to solve for T. So we have 78 equals 26 times e to our k value, and then times T, we want to solve for T, plus 74. So if we rearrange this and then plug it back into the calculator, then we end up with T is about 32. And in this case, our unit is minutes. And that this is rounded as well. So it's in about 32 minutes, it cools down to 78 degrees. And then the last part. Part C says, what will the temperature be after 1.4 hours? And we have to remember that T is in minutes. So 1.4 hours, we're going to find out how much this is in minutes. We know that 1 hour is 60 minutes. And then 0.4 is the same as 4 over 10 times 60 minutes. This gives us 24. So 60 plus 24, we get 84 minutes. So 1.4 hours is equivalent to 84 minutes. So 1.4 hours is equivalent to 84 minutes. So then we're going to plug this in. We have T of 84 equals our 26 times E to the negative 0.0578 times T, which in this case is 84, plus our T sub S, which is 74. So if we plug this into the calculator, we get that T equals 74 degrees Fahrenheit. And again, this is rounded to the nearest whole. So after 1.4 hours or 84 minutes, then our temperature is 74 degrees.